All right, I guess we can get started. This is our seventh talk of the series this year, and we have Michael Hu today to talk about his recent work on mixing in the continual learning setting. And he's a fourth year PhD student at NYU, working with Kim Yuncho and Tal Wilson, and this work is a collaboration with the other people there. Very excited to learn more about it. I know a lot of people in the mixing team have been looking at this paper. There's some discussion on Slack.
Okay.
It, so we're trying to keep it lively, and we'll probably bug you with questions. And let's see how it goes.
Yeah, please do. Cool. So, quickly going through the data mixing problem then. So, we have K domains or like K subgroups in your data mixture, and you're trying to train your model over T steps or some amount of compute. And then, you have, up to T times you can play these distributions in the simplex or like, pick a particular sampling distribution. And the reason why we might want to do this is that, as we've seen over the last couple of years, you can get better scaling by picking a different data mixture than sampling every datum uniformly at random or doing ERM, right? Cool. And data mixing is challenging because we want to find the best mixture efficiently. Like we could just try all, a gajillion data mixes and then, pick the best one and declare victory, but then that would not be the best use. So the first thing that people have tried are approximations. So in particular, like you don't want to train for all of, the compute that you want to use, you may just train part of it, or you use smaller models. Another idea is to try like lots of different mixes online. So you try a data mixture and then you say like, okay, this one's scaling well, and you lean into that. So some representative methods here for approximations are like regmix or like whole mix, and then for the trying lots of mixes like repeatedly, you can like take a look at ADO or Doge. Okay, but today I wanted to talk a little bit of static data mixing because this like algorithm is related to that, like the regmix, data mixing laws, OLM mix type of algorithms. And the idea here is you take a bunch of small scale proxy models, you like train a bunch of like 20 million parameter models. And with these models, you kind of try to cover the simplex, or like the space you want to sample from. And you trained all these models, then you fit some regression model, or you just generally try to model your loss surface from that. And that implies some minimum, and then take the data distribution that aligns with that minimum, and then you say, this is my training distribution. The question here is like, not how densely do you need to sample the simplex? And roughly, it seems to be quadratic. So if you have like K sources, you need at least like K squared proxy models. Cool. Okay, so that's the background. And the goal that we had in this paper was to create an algorithm that would conceptually work all the time. So we want to take K domains and then get some data mixture. And in particular, we actually wanted to start in the middle of training because, a lot of these data mixing algorithms are predicated on pre-training, but, like if you don't want to do pre-training, then you still have data mixing problems. And in particular, just to give you an example, let's say you were trying to fine-tune YNAP. You had 5 sources, and you wanted to do the proxy model thing. That actually doesn't exist, right? There's no 20 million parameter model that is fine-tuned on the same data distribution as YNAP. So there's just some conceptual gap here, or some conceptual gap that's not being served that we wanted to fill. And of course, as with other algorithms, we also wanted it to be cheap. Okay, so the non-existence thing is one part of the small models not working, but also just if we just did some thought experiment, we were training some 3 million parameter model. Is this really going to predict the dynamics of a 70B model or a 700B model? It seems kind of optimistic, right? And indeed, like in like the Olmix 2026 paper, and then this like tech report from Microsoft AI, they actually noticed that there's some breakdown. So like what they did was they took like these smaller models and then tracked their ability to predict the scaling behavior at larger scales. And there is some like scaling trend that is like not super clear. And like they even called out in like the Microsoft AI report that this rank invariance hypothesis, that I can just take good data mixes at like the small scale and just like transfer them zero shot essentially to the large scale, that is not true. It doesn't hold. Okay, so these twin issues with these small scale models. The first one that in fine tuning they don't exist, and then even in pre-training there's some like maximum size that you can like take before like these approximations start to break down. One way you could get out of this is try to set data mixtures online. So like in like the ADO style, or like maybe Doge. I think this is like, just from my sense, it's like a more active area of research, because it's like more involved in terms of like data infra and stuff like that. You have to like change your data mix online. I also did something like this, and I concluded that like the static data mixing is does like fairly well. So that's like the style that I went for in this work. Yeah, so I think this is promising, but perhaps there's some like infra pain and things to work out here. Okay. Right. So want something that works all the time, can start in the middle of training, cheap. That's like the desiderata of this algorithm. And any questions about like the setup here or what we're trying to do? Okay. So that brings us to the algorithm, which we call on policy mix. And the core question is like, how do you efficiently test mixtures without doing a separate proxy model? And our like realization was like, for the whole point of the separate models, you have some pre-trained weights that are like onerous to test, and then you create like a smaller model with fewer parameters. That way you can run it on fewer GPUs. You can run like more efficient experiments, right? You can do a similar thing with LoRa. So let's just say, like the example I gave earlier, you have this like 7 dB model, and then you could put 20 million parameters in a separate model or 20 million parameters in a LoRa. It just intuitively seems to me that like putting the 20 million parameters in the LoRa, it would give you better, more faithful predictions to what's going to happen in the 7 dB model. Right? So that's one idea. The other thing that we wanted to just train one run per data set. So I mentioned earlier this like roughly quadratic scaling like recommendation that comes out of the Olmix paper. You want to like cover the simplex with lots of data points. Ideally, we would just do one run per data set. That way you have like linear scaling instead of quadratic scaling, the number of data sets that you have. Or I was talking to like some folks at Microsoft about potentially using this, and they said that like if you have like 100 different data sets, and then you were trying to do like regmix, then by the Olmix recommendation you would do like 100 or like 10K proxy models. It's a bit onerous. So we wanted to just do one run per data set. So these are the things that we want to do, and then the solution that we came up with was this LoRa plus model merging. So in like some papers that came out earlier, like merge mix or merge to mix, they were making the claim that for a model that has been trained, you can test mid-training mixes by training on data set A and training on data set B, and then you can like simulate the effect of intermediate mixtures just by doing linear interpolations between data set A and data set B. So implicitly, this is assuming some like linear mode connectivity here. You're like on the line between data set A, the model for data set A, and the model for data set B. There's no like huge like spikes in the loss. But this does seem to hold both in their tests and in ours for models that have like escaped initialization. Yeah, so with the combination of these two things, we can do like proxy runs that are like tied to the main model, and then we only do one proxy training run, and then we simulate the effects of like doing intermediate mixes by doing model merging. I'll just skip this slide. Okay, so this is like what the algorithm does. So let's imagine that you already have some data mixture, and then you're trying to add new data sets to your data mixture. So what this algorithm does is it trains a new LoRa for each of these new data sets, and then it trains another LoRa for your old data mixtures. So once you have these like k+1 LoRas, you do model merging between all of these. And doing those model mergings is like simulating the effect of training a new model on that data mixture. And once you like have these like fake proxy runs, you then like find what like the optimum is, and then use that optimum as the training mixture.
Quick question. What if you want to pick the best mixture for training from scratch? Do you train a bunch of LoRa's off of just an initial, like a random initialized model?
Great question. So as I mentioned earlier, you probably don't want to do that because you wanted like the linear mode connectivity to kick in, right? Yes. So what we do is you just train a little bit with ERM. So you take data uniformly at random. Mm-hmm. And then once you do that, you can just run this, like the old data mixtures with ERM, and then you do the adjustment.
Sorry, so that is over the full set of candidate data sets, or just like some reference data set that you're sort of looking to be like what's, yeah, I guess I still totally covered how you pick data mix that you're using for the base model that you're then going to LoRa over.
Yeah. So in the pre-training case,
mm-hmm.
And I guess like I'll say a little bit more later, but let's just, so in the pre-training case, you have like your data, mm-hmm. and then what I'm saying is start off by sampling each document with uniform probability.
Okay, cool. That makes sense.
And that will give you the old.
Yes.
Okay, cool.
I have another question. So when you talk about the linear mode connectivity kicking in, did you do any experiments that test like how close does the alpha merge match the alpha data on the LoRa itself or the national one?
Yeah, great question. I have a slide for this a little bit later. Okay. Yes.
So for the LoRa weights, are they? I mean, in orthogonal subspaces, for example, like you can have different data mixes in
mm-hmm.
different spaces. If they are orthogonal, it mm-hmm. would make sense. But like if they're coplanar, mm-hmm. why should like any arbitrary linear combination give you a good model? So it kind of like goes more to the model merging question in orthogonal subspaces mm-hmm. versus in the coplanar subspace.
Yeah.
But yeah, I was just wondering if you guys.
Yeah, also great question. I mean, I think there's there could be like better variants of this algorithm. However, because it's low rank, it's probabilistically orthogonal mm-hmm. for like random, So I think that's like my answer. Like we're training in almost orthogonal subspaces when we do like randomly sampled LoRa's.
Okay, but there's no explicit.
Yeah, but you can imagine like you partition the subspace and then maybe that helps. I haven't done that experiment, but yeah, that is interesting.
Also, like, how do you get like if you have the best mixture? Like, how do you get how do you pick the optimal mix? Like, how do you get the?
So once you have these values, you treat the like once you have actually this might even be worse. Once you have the merges, you'll have like the merge weights to loss values, and then you just plug that into a regression model.
So you're using a regression.
Yeah, so you're fitting like the scaling law based off of these like pseudo runs.
Kind of just to be like super small set. Alpha, like in this case, the alpha just ends up being the mixing parameter for the data set.
Yes. Okay.
I have another question. I was just wondering of an adversarial situation where two data sets are basically the same.
Mm-hmm.
Like, what would the alphas look like in this case?
then I think like it could be like 90-10, it could be like 50-50. It probably would
I
like all of
think
those
you
are
just have a flat region in the loss space along those two data set axes, right? So like you could move, like anywhere along that line and you would have ISO loss if those data sets are truly interchangeable, I think.
Yes, but if this is working exactly like, because the coplanar thing like made me think
Yes.
there's this honor that if I put two data set, would it actually do that? The algorithm or
That is a good control.
What's the reason for it for not selecting 50-50?
Well, so like I think what would happen is like you train both LoRa's, right? And then so like if you train both LoRa's, it'd probably just be like a flat line. So like your LoRa A gets like 3.1 loss, LoRa B gets 3.1 loss, and then you merge and it's like all the same. So then I think like the optimization for like those two data sets would just be like somewhere in the
That's
middle.
a nice trick though that you could use to calibrate this specifically in terms of like what's the noise tolerance or like what's the sensitivity, like how small the LoRa could you use.
I mean, this doesn't show promise in 2, but when we make it K, the key only 2 are hidden.
Yes.
Then it starts becoming interesting because
Yes.
can the regression model that you're training actually figure out within the K linear runs that actually 2 are basically the same variable.
Yes.
But also there's a duplication question over there,
Yes.
which I will not like bring here, but like they're basically the same data set. Like actually there's some loss of by just repeating it twice. So maybe the equal it's not actually cleaner in that way.
Yeah.
But that's obviously not useful.
Yeah.
No, that's interesting.
Okay. So like what do these like moves give us? The first one is that you can adapt to new data by like training like the K+1 LoRa's. And the second one, there's no separate proxy model. Like all the proxies are tied to like the main model, which is why we call it like on policy mix, because there's no like separate proxy model. There's like forecasting performance. It's all like tied to the main model. Okay. So I guess like we have had some discussion, so I'll move on to the experiments. The first thing that we're checking is like, is this like a reasonable thing to do? So in our tests, the predicted loss surface tracks the true loss surface pretty well. And here, like the LoRa loss is going to be a bit higher because we don't train for as long, and it's a LoRa, but we just want like the shapes to be similar. So the true loss surface minimum and the predicted loss surface from this like LoRa plus merging operation seems to be like pretty well correlated. Yep.
In this case, when you have the true loss surface, you are actually doing full fine tuning on the mixture, or you are still using a LoRa.
Yeah. So how do we create the red line? So I just trained like all of those mixtures to completion.
Okay. Okay.
Yeah. So let's say I was like my budget is like 500 flops, then I like dedicate like 500 flops to each of these runs. Versus like the LoRa thing, I'm like using some fewer amount of flops plus the merging.
Okay.
Okay, and then we did some like pre-training and continual learning experiments. So for pre-training, we do like the doing nothing baseline or ERM. We also do merge mix, which is technically not supposed to be done for pre-training, but like we for both for our case and this case, we do like 20% ERM as like a warm-up, and then we do like the merging. So here, like this is sort of like our algorithm, but like with full fine-tuning, or sorry, full training instead of like this LoRa thing. And then we do like a proxy model variant where we like try n squared or k squared different proxy models and then fit the regression from there. And then for continual learning, we do like this like warm-up stable decay baseline that was recommended from like a couple years back. There was also this paper out of Apple called like scaling loss for forgetting or something, where they like recommended that you do like 10% cutting in old data for continual learning, and that sort of mitigates forgetting from pre-training. So that's another baseline. And then in cases where it's appropriate to do so, we also do like on policy distillation for like instruction tuning setting.
When you say on policy distillation, because you also say SFD training, or distilling from a lot of models?
So
policy distillation.
yeah, on sorry, this should say on policy self distillation. So this is this is an algorithm for like instruction tuning settings.
Is it like, okay, is it instruction tuning is the on policy learning algorithm, or you create on policy data and then you put SFT on the on policy data?
Or yeah, I can pull up the diagram later, but like the
Okay, sorry. Yeah.
or just answer your question, like the like in this particular algorithm, the way it works is like you have like some prompt, and then you create like a bunch of different rollouts from that prompt, and then you like you like ask the model like what or and then you have like a separate model as a teacher that has the answer.
Okay, so it's on policy distillation.
Yes, it is on policy.
Because sometimes people call self distillation to SFT on the on policy data.
I'm
you use the model,
talking
you create
about
SFT data, and then you train the model on this one data with some other mixes.
yeah, I'm talking about this.
Okay. The teacher student on policy distillation.
Right. Okay, and then for like additional setting details for pre-training, we did like the one epoch at like chinchilla optimal, and here we're like mixing together different data sets. And then for continual learning, we were introducing the data sets in sequence. And then yeah, the goal would be to like minimize the new data set without forgetting the old stuff. Okay, so this is the pre-training results. So yes.
What's in the validation data
For pre-training?
for both?
So the validation data here, I think it was like it's just like the ERM like distribution.
So the goal is to minimize all of them uniform.
Yes.
So no actually that's just NTP.
NTP?
Just like next to prediction on the general data.
Yes. Okay. So here are like the pre-training results. So the gray line is ERM or doing nothing, and what's it? So both the merge mix and OP mix tend to be better than the OM mix. All better than doing nothing, and then I think merge mix is slightly better than OP mix, which is, to be honest, expected because like with OP mix in this setting, it's just like basically an extra approximation on top of merge mix. Okay, and then we did some like downstream evals, and I think like OP mix is like slightly better than ERM. But yeah, this is I guess we don't optimize for this, so I guess it's maybe just a sanity check.
Yeah, so we're gonna ask like you don't really optimize for the evals. So like
Yeah, we're just
should
optimizing.
it
Yeah.
be better?
Yeah, so I guess it's like the vowel loss is probably correlated with
With the evals.
yes.
So for Olmix, how many points did you sample? I mean, it says quadratic. I mean, did you?
Yeah, we sampled according to their recommendation. So I don't exactly recall, but yeah, something on the order of like X squared.
Okay. And do you think like this Olmix failing is because of like the scale problem that it is not transferring across the proxy small nodes? This is the big one, or in this case, you actually trained for the same size and didn't really transfer it at all?
Yeah, so we also we also used the recommendation for like a 30M model. I think like that's what they said. I don't really know why it's like much worse. I mean, it's still better than doing nothing. So yeah, I'm not sure.
And did you also try a uniform baseline where you actually just weigh the buckets uniformly? But doing nothing is basically in the size proportion.
Mhm.
But
Sorry. Like in this case, we do like we do sample from the buckets with equal probability.
oh, so doing nothing is like same weighting.
Yeah, we kind of pretended all the data sets were the same size.
Okay.
And what size is the LoRa? And does it matter?
I think the LoRa rank was I think 16. I'm not 100% sure how large it was.
Do you think this can also generalize if you start repeating the data? Because you assume infinite data aside, right? Because you never repeat here, right?
Yeah. So going like there's I guess the one paper on this would be like the scaling law repeating data thing, right? So I think you would see like the improvements start to like just slow a bit, but I think it would still work because like the way this algorithm works is like you just train the LoRa and then you see what the loss will be, and the like the overfitting doesn't kick in for like a really long time, like over the number of epochs. So I think it should still work.
I think it's also like with small
Because I feel
models,
like,
with small models you can repeat a lot more. So that might be a bit of a coco flora that doesn't have enough parameters to start over. Whereas the big models like
which means a lot of model will overfit fast.
it doesn't have enough parameters, right? Like big models tend to memorize.
So I don't think it's, so sorry, I wouldn't say the opposite thing. The normal model might not be able actually. Here, he did not learn everything because the data was big enough, right? But what if you start repeating the data?
Are you thinking about repeating the data in the pre-training setting or like
Yeah, in the
what's
pre-training setting here.
Yeah, that's what I was saying. Is like in the pre-training setting, like the overfitting doesn't kick in for a long time. Like you can do like multiple epochs. So I think
No, I'm talking about repeating the data in the pre-training for some sources, but not for all of them.
yeah, like you can do multiple epochs over various data. Like
Now here they have a single data set and then they repeat that data, right?
Mhm.
But they don't have, for example, 10 topics on 10 sources, and then they repeat one source 5 times while repeating the remaining sources 1 time.
I see.
Which is,
But I think it would like the individual loss curve would be similar to that. So like basically for LoRa, we're trying to like get a sense of what this curve looks like. So like let's say I was like I had some source that I wanted to do 10 epochs over. Like presumably you would still like in pre-training at least see like some dynamics like this. So then your LoRa would still be able to fit that pattern. Okay, cool. Right. So in continual mid-training, the setting is we like trained on each of these data sets like one at a time. So we took this like off-the-shelf model and then we trained on these data sets individually. And here the gray line is actually the retraining baseline. So so like we dedicated a certain amount of compute to like training on each of these data sets, and then the gray line is if we like took 5x the compute and then trained on all of them. So it like or like the goal is to get closer, ideally even beats the gray line. So continual SFT tends to like have some forgetting, and that is indeed mitigated by doing this like 10% data replay of like the previously seen data. And then our baseline which like you know will adjust the data mix. It's not just like you know outputting 10%. It like does the best at mitigating forgetting.
So the previous data is uniform mixture of the bottom file, or
so in the 10% replay case, yes, it is a uniform mixture. In our case, we use like the mixture that we computed before.
and then you're independently doing SFT in each domain.
Yes, in the continual SFT, it's like without any data replay, like one at a time. This is like maybe like a different way to visualize this, like the continual SFT versus OP mix. You can see like there's like more forgetting done by continual SFT, and this is like this is like the you know recommended learning rate schedule, so it's sort of like a tuned SFT baseline.
Can you clarify what is the objective that OpenMix is trying to optimize for, let's say, at the 30,000 boundary?
Yes, so there it would be, or like just starting on Reddit, it would want to reduce the loss on archive, OpenWebMath, and Reddit uniformly.
Okay. And for continual SFT, the goal is to just find your, I guess, right?
Yes, just fine tuning on Reddit.
Understood.
Okay, and then we did like a third experiment on instruction tuning for like data sets of size like, I don't know, roughly around 1,000. So in this setting, because it's instruction tuning, we can also use like on-policy self-distillation. And the way it works here is like you have like a teacher that knows the answer, and then it like, you know, you KL distillation from the teacher that knows the answer to like the student that doesn't know. And then like the student will like generate various rollouts until it, you know, gets the thing correct. And so here are the results. We took this setting from the self distillation fine tuning paper, and there they trained on like medical and then science and then tool use. So we just did the same thing. So here, I think the thing to note here is that like OP mix like roughly matches the accuracy of self distillation fine tuning. And of course, you can also just run OP mix to do data replay alongside self distillation fine tuning, and that does even better. And I think these are like I actually like did a bunch of like work to match the results in their papers, so these are not sort of like worse results.
So like now you've moved to optimizing for accuracy, or you're still optimizing for the loss but testing accuracy?
Yeah, good question. So in this case, it's optimizing. It's trying to minimize like the error rates, like the average error rates over all these data sets. Yeah. So yes, I am optimizing for accuracy.
And does like optimizing for a hard metric change anything, or you feel it's like as like the optimization is just me in that way?
I didn't notice any like issues. I guess the way it works would be like when you're evaluating the lures, instead of taking the loss, you just like, you know, do that accuracy.
Yeah, I guess since you're CPTing a model, like it has some capability already,
Yeah.
so it like really de-risks that part of like.
Sorry, maybe I missed this. What's the size of the base model that we're doing this off of?
This is I think 1, 2.5. So
Okay, so there's like a good solid foundation there. Interesting.
And so like in this case, you don't know the baseline data set that Quen trained on, right? So do you use an approximation there to replay, or?
Yeah, so that I don't even use. Like,
They just use the test sets from all the popular evals.
So that's what Quen.
Yes. Out of curiosity, what is the performance of just the base model without any of the like, you know,
I think it's like
training?
if I recall correctly, I think it's like 0.5. It's like slightly under like the continual SFT for like top left bar.
Okay, that makes sense. I wouldn't be, you know, sometimes the training can be a little finicky. Like, you know, you end up with experiments where the base model is better because you can't approximate its training distribution when you're doing, you know, CPT or something. So interesting. That's cool.
How will it scale with more like domain sources or like with more domains?
Even this algorithm in general.
Yeah.
Yeah, I've not tested that. One of my collaborators is trying to do this for Vine, and so I think like the truth of it is I don't know yet. So I think like if you find the like if you find it annoying, like let's say you find like doing this over 100 data sets annoying, what you could do is you just like run this algorithm for like just the math data sets, and then you create a distribution, and then you collapse all those into one, and then you like run this algorithm again. So like I think there's like so I guess like you could just run this algorithm out of the box, but like when we're talking about with the 5 people, like you can also like run this like multiple times, you know? So like you determine like what the data mix is for like each of these various subdomains, and then you just like add it together. Yeah, so I don't know, that's just like what we're thinking about at this point. Okay, so on the efficiency side, generally, OP mix is more efficient. So, you'll use less compute doing these approximations, especially in the continual instruction tuning case, because for on policy self-selection, you do like a lot of rollouts. Another question I got was like, if you like if I wanted to spend more compute on OP mix, can I do that? And the answer is yes. Like you can technically just like run it again, as I was saying. Like you have like some mixture that you're happy with, and then you just do it twice during training or something like that.
So when you say do it twice, you're saying that like get some, and let's say you're starting with pre-training, you did ERM till some point, and then ran OP mix, get one set of weight, train for longer on that, and then again repeat the process. Is that what you're saying?
Yeah, exactly. Like let's say you just wanted to like check it in the middle or something like that. You have the ability to do that, and then you can just like fold the old mix into like the new like the M plus one, the K plus one LoRa.
Did you just try to fit the model at like one scale of parameters that you're using, or did you try to like, if the training went on, like fitting at multiple places?
We did not try. We just set the LoRa to be of one size, like size 16. Yeah, I'm not 100% sure how it scales with the LoRa. Going back to your point though, there might be something where like you want these to be orthogonal. So that might be a thing to look out for. Like, does increasing the LoRa size destroy like your ability? Does increasing the LoRa size like affect this picture? Yeah,
In
that's
this
it.
particular case, you're doing two at a time for this particular.
In the top, I'm doing 2 at a time for these 2 data sets, and then in the bottom, it's like the continual thing where I've like trained on a couple and then I add a new one.
Do you wonder how much does the base model influence these things? Like assuming a base model knows a lot about the data already, it's probably less learnable on some tasks. Like let's say Quen is like benchmark on Amy for instance. And if I wanted to use that to get a data mix for Amy, it'll probably like the way you validate because it doesn't see much progress. Adding more similar data. How does like one explain away the base model effect? Or is there none?
Well, I feel like maybe the generalization of your question is like how like is like does like the data invariance thing hold? So in the experiments that I ran, like I actually like was like arguing with like Patricia a lot about this because like
Different Patricia.
Huh?
Patricia?
Patricia, yeah. Or like one of my co-authors a lot about this. Like she wanted to like more emphasize the fact that like that this like might be better for like skipping the data or like the invariance from like small to large thing. We observed that there is like some change in like the optimum from like 150 to 530M, but it's not huge. But I think like it could, and like I think Laura is like probably better served to identify that than like a separate proxy model. But I don't have any evidence, strong evidence for that.
I guess like if you're doing continual training, then you can just use the same model. So it's almost like a no-brainer that you have evidence of modeling for this particular model. But if you're using this to generalize to something from pre-training, then potentially you want to do something like a small amount of ERM, and then it's a different capability class.
Yeah.
So you can kind of branch out from different base models, depending on that, or not really.
Sorry, I didn't.
I was thinking like if you wanted to like take insights from this to use for pre-training from scratch, would you like? I think you initially recommended you should just do ERM on like a mixture for a bit and then start branching off with lower amounts. That is more informative than CPT, like taking a well-trained base model and then doing your own.
Yeah. I like it seems reasonable that like maybe warm starting it in the way you described could work. Yeah.
I think that way it would also avoid the situation where like certain base models like llama base versus ON base or mixed trial might have like a completely different distribution over the buckets, and then you're like, okay, what should I choose?
Yeah, that's a good point. It seems like I think that's might be a good idea. Like because like if you know like roughly what the good data mix should be, then you can just start with that and then like maybe like adjust the mixture like with OP mix later.
I have a very basic question just to make sure I understand everything. The model you use for LoRa training is the model you use for selecting the weights. Is it the same model you train at the end of the data mix?
Yeah. So after we train the LoRa and then get essentially the future loss projection, we throw that LoRa away.
But you train the same base model.
Yes, and the base model is the same.
Do you think the weights? Okay, so the weights are tied in some way to that model, right?
Yes, the LoRa weights are tied to the model you're interested in training.
Okay.
So you're saying that the best data mix is like based on the model and not like only the fact about the data?
But yeah, that's exactly what I'm saying. Or like going back to this picture, like the LoRa is essentially enjoying the representations of the base model, whereas like the separate model does not have that advantage. Yeah, so if you had like 3 million parameters for a proxy model you want to put, I would argue you should put it in the LoRa rather than putting it in the separate model.
One more question. So in this particular case, like once you have like these mixture like alphas, what model are you fitting to predict the loss? Because eventually,
It's the same question, right?
Yeah.
oh,
What? Sorry.
It's asking what model are you using to fit the loss?
fit from the mixture, like because you're
I think,
basically
are you asking for about the regression model?
yes,
or-
yes, that's what I'm saying.
Yes.
You
So
can, I mean,
you can use your favorite method.
no, but like, I mean, for in this particular, I mean, case, where you were in two at a time, I mean, naturally the curves look quadratic-ish with like a wide basin.
Mhm.
So I mean, like linear model must not make sense right over there because it would always have like the minimum points over the edge boundaries of the simplex. So
yeah, good
I'm just
question.
wondering, like, if we arbitrarily increase the capacity, or like even a one hidden layer neural network which has like more capacity, strictly speaking, do you feel that it will cause like some weird overfitting issues or some regions in the simplex which are highly confidently incorrect?
Yeah, so it's not exactly linear regression. It's log linear regression. So
It's linear log space.
yes, log linear regressor, and this curve is like a composition of 2 curves.
Mhm.
So you'll have like one log linear going this way and one log linear going the other way, which is why it looks
Summation
quadratic.
is like this.
Yeah.
Okay. I think that's what open source is like.
Yes. Yes. Yeah. Yeah. I also recommend using log linear.
Okay.
So before OLM mix or OLM mix, there was like a paper called Aioli where we were saying that like everything is actually doing like log linear stuff. So, so yeah, I think that still holds for the static weight mix. Okay, so takeaways. So with this algorithm, you get ideally efficient data mixing at any point during model training, and the 2 tricks are using LoRa and then doing some model mergers.
Can I ask one last question?
Yes, please.
If I ask you to list the benefits of using LoRa here instead of doing full fine tuning, apart from compute, if you just like now we want like to predict or list all the hypotheses we have for why it works with this LoRa.
Yeah, so I think in principle, like if you wanted to spend the compute for full fine tuning, then I think you can definitely do that. Yeah, I think in our results, like the doing the
I
LoRa,
just have a hypothesis that maybe training initialized parameters like the LoRa parameters might be doing something useful here.
They
I-
might merge the non-LoRa bits, right? Like they won't like just alpha add each other if it's a full fine-tuning.
No, I'm saying comparing full fine tuning to LoRa fine tuning. In LoRa, there is some parameters that you initialize here, and I'm just trying to ask or like just like I'm curious if actually training initialized weights like the LoRa weight instead of fine tuning weights like full time fine tuning, if that is giving LoRa benefit over full fine tuning.
I don't think it's giving a benefit.
Yeah, that's, I mean, my understanding is that Laura, what's the, Laura learns less and forgets less. I suspect you could probably do something similar, you know, like if you want to preserve or forget less, just turn learning right down or don't train for as many steps if you're doing full fine tuning, but
For
I
example,
imagine.
one example, just a hypothesis, if the model is already trained on the data, using a model trained on some of the sources to do model ranking and select weights might just like bias the selection. And I feel like LoRa is just will be rubberized against it because you still learn some new parameters. It's just a hypothesis. I guess I invented this like hypothesis now.
Yeah. Or
It's just a hypothesis. You know what I mean? I'm just curious if there is something here about LoRa. I mean, aside from it just being faster, is it like a pure efficiency or compute trick, or it might be just like a trick there?
yeah, so yeah, the question is like why Laura, and the question and the reason was to like generate this plot, like that we can like sort of beat the mixing methods. And so like it goes back to what I was saying, like if you had like 20 million parameters, which you put them separate model or like in the LoRa, and we were arguing like you should do it in the LoRa, and
You
then,
did
like,
LoRa definitely.
yeah, that's why. But as you say, and also as you point out, there could be some benefits to LoRa that I am like glossing over. But I think like from what I observed in the experiments, it's like in particular in pre-training, the difference between merge mix and then OP mix, not like LoRa was not better than merge mix. So
Also, in this situation, all of the buckets that you had were roughly independent-ish, in the sense that they're not indifferent to that, like capabilities. I think like the question that you asked, like if you have a hypothetical duplicate bucket, if you're trying to fit a regression model over there, in that situation, you will, let's say you try to solve it optimally, if the system is determined, you will have rank deficiencies in the inversion problem. So that is one way you can kind of figure out like, okay, there's no solution. So, I mean,
so
it's a linear.
in pre-training, like doing the 20% URM warm-up, like you're technically there's still like the same amount of data sets. So we are like doing like the duplication thing, not hard duplicates because it's like new data, but we are doing that, and I didn't notice any like issues.
Oh, also when you're finding the optimum weight, what regularizer are you using, or I mean, in the sense that so that it doesn't always drift away to the true local?
Yeah, great question. I use like the KL. So basically, I'm calling like the OLM mix as like a subroutine.
Okay.
Yeah.
KL with uniform?
With in this case, it is uniform, but I would do it like the 2 ERM. Yeah.
I guess like just rounding it out, I guess there are two parts of this work. Like one which show that you can reduce complexity quite well when you have a few data sets, and then one which show that on top of when you are CPTing it, you can increase accuracy also. But if I was to reconcile these two together and now start from the beginning, from pre-training, when you're starting with pre-training, people often care eventually about the accuracies, let's say on a few benchmarks. And how do you like use all of that, these three things together to like propose or like use more? I think model merging makes a lot of sense. It just reduces the complexity of number of experiments so much. But how can I use this on a model from scratch? Like, what are the best things? Where I care about accuracy, it is very hard to calculate for untrained models, and so LoRa will just be like random. And then, yeah, I guess That's my question. Like, what would you do if you were using all of the things that you have learned
I
from
see.
this experience?
Like, are you thinking about like cutting in data earlier during training, or like maybe there's some like specialized capability that you want?
Let's say you care about math and code, for instance, and then all of these evals are very like, I mean, generated. You need to like generate some responses and then someone checks them. So like the accuracy is kind of like not a great signal, especially on a barely trained based model.
Yeah.
Do you think there is a way to like massage like the merging idea to pre-training itself? One thing is you can just use Quen and then assume that it will transfer back. That's the most obvious way to like, but that's like where we start from.
Yeah. You could honestly just like do this multiple times. Like as you say in the beginning, like all your like accuracy is gonna be at 0, so it's like sort of fine.
Yeah.
Like you'll just like get mixes, and then like it won't really like if everything's 0, then you'll get something close to ERM. And then like once it starts working, then you would like lean more into the things that are helpful.
I see. So like you keep running the same pipeline during training at multiple times.
Yeah.
And you update the mixture with based on like whenever the model is ready to accept some capability.
Yeah, I think like if you like take some checkpoint, you could just like try it.
Do you expect it to like kind of jump the weights quite drastically? Because like if you keep on continuing these things, let's say, I mean, if in training, let's say for 1 trillion steps, and you only have like 3 times in this situation, do you expect it to like have rapid jumps in the mixture?
You wouldn't have huge jumps because the old is still in here, So like you have like the k+1 floor on the old, and then you're interpolating to it. So your old is still gonna receive some weight. Yeah. So it's still like the old, like the data mixture from the previous round is still present.
Okay. It's in like some sort of like a moving average style kind of.
Yeah, so maybe like just like to your question, like what are the learnings here? The first one is like like I said before, like this like LoRa plus model merging thing for efficiency. And the second one is here like doing this like mixture expansion exercise, and then like folding in the old as like a +1 LoRa.
I have a question. How many merges do you do? Like, what is the number of P that?
So here we did like quadratic merges, just like the number of merges, we just set it equal to the number of proxy runs that OLM mix recommended we use. Yeah, there just to be fair with the number of proxies.
All right. I guess we are at the end of this talk. We'll thank Michael for like telling us about his paper.
All right, yeah, thank you for having me.
Thank you very much.